I am Dr. R. Muthucumaraswamy, Professor and Head, Department of Applied Mathematics, Sri Venkateswara College of Engineering. Now, I am going to take the concept of one-dimensional heat equation. The more general form of one-dimensional heat equation is given by dou U by dou T equal to some alpha square dou square U by dou X square. So, this alpha square is a proportionality constant, so which is nothing but K by rho Cp. So what is K? Is nothing but thermal conductivity of the material. You can take a rod, for example, or wire. Heat transfer in a wire or rod is a very simple example, and rho is a density of the material, and Cp is specific heat of the material. So this is what the constant. Okay, for we are going to analyze the finite difference solution for this particular equation. As before, how to classify this PDE? Let us rewrite the equation alpha square dou square U by dou X square minus dou U by dou T equal to 0. So when you classify, we are going to focus on the second order partial derivatives. So A is alpha square, B is 0, and C is also 0. Please refer our previous lecture, then you know how to take the classification. So B square minus 4AC. So this value is completely 0. This comes under a parabolic family. So it's very clear, one-dimensional heat flow is a parabolic family. Okay, we'll go for finite difference solution. As before, I'll rewrite this equation. So dou square U by dou X square equal to 1 by alpha square dou U by dou T. I'm going to name this constant as a single constant. So dou square U by dou X square equal to A dou U by dou T. Now we are going to analyze the finite difference solution for this particular equation. So we'll rewrite this equation using finite difference form, as we know very well how to take the finite difference equivalent for the second partial derivative with respect to x, ui plus 1j plus ui minus 1j minus 2uij divided by h square on this side a. So dou U by dou T, I am going to take T with reference to maybe y-axis. So instead of y, I am taking a dummy variable T. So I'll rewrite the finite difference form uij plus 1 minus uij by k. I am using forward difference for this case. Of course, dou U by dou T, uij plus 1 uij. When you take the finite difference solution equivalent for second partial derivative, so our focus on this point is uij and ui plus 1j and ui minus 1j. The step size along x direction is h. So sum of these two minus 2 times of this divided by h square. That is what the finite difference equivalent. Now we are going to cross multiply. Let us rewrite this equation first. A uij plus 1 minus uij by k equal to ui plus 1j plus ui minus 1j minus 2uij by h square. So we'll cross multiply. So uij plus 1 minus uij equal to k by ah square ui plus 1j plus ui minus 1j minus 2uij. Okay, j plus 1 equal to uij plus lambda ui plus 1j plus ui minus 1j minus 2uij, where lambda equal to k by ah square. So I'm taking this entire thing k constant lambda. So let us simplify these two common coefficients. So uij plus 1 equal to 1 minus 2 lambda. I think you are able to understand. Uij minus 2 lambda uij. If I take product, you will get 2 lambda uij minus. So I am combining these two terms plus lambda times ui plus 1j plus ui minus 1j. These two remain. This is what the finite difference equation for given one dimensional heat equation. Now in this case, this is uij. I'll rewrite the equation separately. Ui j plus 1 equal to 1 minus 2 lambda uij plus lambda times ui plus 1j plus ui minus 1j. Okay, now our aim is to reduce the scheme into simpler form. So this investigation done by Schmidt, well-known mathematician, he suggested dilute the coefficient of uij. To dilute the coefficient, I am going to take this entire constant 1 minus 2 lambda equal to 0. Therefore, lambda equal to 1 by 2. If I substitute this value in the above equation, so you will get ui j plus 1 equal to, this entire thing tends to 0. You will get here 1 by 2 times ui plus 1j plus ui minus 1j. So this is what Bender-Schmidt finite difference scheme. We'll discuss later on what about Bender-Schmidt scheme. Let us analyze this molecular structure of this entire finite difference equation. What is explicit scheme? Thus I'll explain first what is explicit scheme. The method of finding out one unknown value at advanced time level using the known values at given time level is called explicit method. See here, a simple diagram is given. So you know this nodal points. Of course here uij is a point, forward direction ui plus 1j, one step along x direction positively, backward direction so I minus 1j. So these two values at known time level. So these two values I am taking known value. I want to find out one value at advanced time level. So if you want to find out one unknown value at advanced time level using the known values at given time level is called explicit method. So this finite difference scheme according to the Bender is nothing but what we have derived already, the outcome of this result. Uij plus 1, 1 by 2 times ui plus 1j, ui, that is average value of these two. We have already ignored uij by setting lambda equal to 1 by 2. So we will take only the extreme values of uij. So this scheme is called Bender-Schmidt finite difference scheme. We will do some numerical problem for better understanding. Numerical problem based on the Bender-Schmidt finite difference scheme. So solve dou u by dou t equal to dou square u by dou x square with u of 0 comma t, u of 1 comma t equal to 0, u of x comma 0 sin pi x, and the material length is 0 to 1. Compute u up to first 5 time steps. So our aim is to find out the numerical calculation up to 5 time steps. The method is not given to you. The material length is 0 to 1. Yes, that is given. The temperature at these two extreme values set to 0. That is what given. And this temperature distribution most probably is a sinusoidal. So that is what the temperature distribution is sinusoidal. That's what they mean. Okay. So In this case, you know the finite difference scheme. I'll recall uij plus 1 by 2 times ui plus 1j, ui minus 1j. Very first step, I'm going to use Bender's schmidt. That is in my mind. Now, what is a equal to 1? Of course, here a equal to 1, the coefficient of dou u by dou t. According to our theoretical model, a dou u by dou t. So, a is 1. So, lambda equal to k by ah square. This referred from the previous book work. So, I am setting lambda equal to 1 by 2. In order to reduce the entire scheme into Bender's schmidt, so I am going to take lambda equal to 1 by 2. So, lambda equal to a is also 1. So, 1 by 2 equal to k. Therefore, k equal to h square divided by 2. So, if I choose the step size according to our material length, the material length is 0 to 1. So, you can choose step size in different form, 0.2. So, if you take 0.2, you know how to split up 0.2, 0.4, 0.6, 0.8, 1. Or otherwise, you can choose step size 0.25, 0.5, 0.75 and 1. So, this is the way you can select. So, the better choice is either 0.25 or 0.2. So, let us choose 0.2. So, k equal to 0.2 whole square divided by 2. So, numerical value is nothing but 0.02. So, this is what the k, the numerical value. So, this is for time step. I want to execute the calculations up to 5 time steps. We'll form a table because all inputs are ready now. We'll go by numerical table of values. So, this is x, t, step size along x direction 0. I'm choosing 0.2, okay, 0.4, 0.6, 0.8, 1. Along time, okay, 0, 0 0.02, 0 0.04, 6, 0 0.08, 1. So, x is the step size, h, that is along x direction, h is the step size. The material length is 0 to 1. So, I am taking the step size 0.2. So, 0, 0.2, 0.4, 0.6, 0.8 and 1. Similarly, time step k, we have calculated 0.02. So, we are supposed to find out up to 5 time steps. That is, this is initial time step, first time step, second, third, fourth, 5. Given condition here, u of x comma 0 sin pi x, let us complete the initial time level, that is at t equal to 0s. Now take x equal to 0, sin 0, 0. Now sin 0.25 is 0.5878. Please remember, you have to use calculator using the mode radian. And then at 0.4, give x equal to 0.4, 0.4 into pi sin times, so 0.9511. Now you can check, yes, this is duplicated. Since it preserves symmetry, of course you know the sine trigonometric function is symmetric about 0.5. Now this is a condition given to you. Now how to find out remaining time level? Of course, initial time level set to 0, that is given to you, and extreme corner also 0. Now we are going to calculate the intermediate value. If you want to find out this value according to this scheme, average value of the previous time level, that is, you just ignore this node, average value of these two is nothing but this. Please refer our book work, you'll get an idea. So 0.4756, the next value 0.7695, 0.7695, 0.4756 and then 0. Similarly, you can repeat the calculation by taking average value of these two so which is nothing but 0.3848, 0.6226, 0.6226, 0.3848, and then 0. Similarly, at t equal to 0.06, the average value of these two, 0.5037, 0.5037, 0.31130, and then 0.08, 0.2519, 0.4075, 0.4075, 0.2519, and then 0. Finally, I am going to calculate the last time step at t equal to 1, which is nothing but 0.2038, 0.3297, 0.3297, 0.20380. So you will get a final answer at t equal to 1, u of 0 comma t equal to u of 1 comma t equal to 0, and then u of 0.2 comma t is same as u of 0.8 comma t. Now you see these two values are duplicated, so you can simplify in a better way, and then u of 0.4 comma t, 0.4 comma t, these two values are identical, so 0.4 comma t, 0.6 comma t is nothing but 0.3297. It's a very standard problem, a solution of one-dimensional heat equation. We'll do one more problem to gain some confidence. And one more thing I want to say, from this table is very clear that initially the temperature, the extreme ends are 0, 0.5878951, of course. Now you see the temperature gradually decreases. That means whenever any heat transfer problem, there is a heat transfer from one medium to other, there is a heat loss. That is an indication the value decreases gradually as time advances. Next, we'll do one more problem for a better understanding. Let us take the problem solve dou u by dou t equal to dou square u by dou y square with the condition, boundary condition, u of 0 comma t, u of 5 comma t 0, u of x comma 0 equal to x square 25 minus x square. The material length is given, time positive. I want to calculate u up to first 5 time step. We'll go by the Bender schmidt. It's a simple model. Here also the coefficient A is 1. You know what is K, as we have done in the bookwork. K equal to A h square by 2. A is 1, therefore h square by 2. Since the material length is 5, okay, 0 to 5, I'm going to take a step size 1, 2, 3, 4. So the step size is 1. So therefore k equal to 1 by 2.5. Now we'll go by the explicit scheme, Bender schmidt scheme. You know the step size, that is what? 0, 1, 2, 3, 4, 5. Time step 0.5. This is k and this is h. Now the first initial value from this condition I can deduce by setting x equal to 0. This value is 0. Now give x equal to 1. 25 minus 1, 24 into 1 square, 24. Like that. Put x equal to 2, you will get 84. Put x equal to 3, you will get 144. You can check. Put x equal to 4, again the value duplicated. And finally this boundary condition is given to you. Now we'll adopt the same procedure. This is 0. Now I want to calculate this value. Skip this node, take the previous level, average value of these two, you will get 42. Next, I want to calculate 84. Average value of 24 and 144 leads to 84. Repeat the procedure in a similar way, you will get fifth time level. Remember, don't take initial time level. 1, 2, 3, 4, 5, fifth time level. Stop the procedure at time t equal to 2.5. You know the outcome results. As the same thing you can observe as temperature, sometime you know there is a fluctuation. Here you see 24, then the value increases. It depends upon the boundary condition. Why? Because the other extreme side is maximum compared to this side. So that's why there is a fluctuation. Normally the trend is decreasing, here increasing and then slowly decreases. Normal, this particular extreme temperature influence this one. That is the reason why the increase then and then gradually decreases. So very interesting thing, outcome of this table, numerical table. As temperature, as time advances, temperature decreases. That's a usual normal heat transfer problem. Thank you.